All right. Hello, everyone. Sorry about that little snafu. As mentioned, I'm the program manager for the hydrogen technology area within the Office of Energy Efficiency and Renewable Energy Hydrogen and Fuel Cell Technologies Office. As you've heard this morning, it's been an exciting 2 years since our last AMR. We have a lot of interest growing in hydrogen globally, with countries developing roadmaps and strategies and calling for investments in the equivalent of billions of dollars for the deployment of clean hydrogen production technologies, as well as required infrastructure to enable the hydrogen to be used to help decarbonize a number of sectors of the economy. We have countries which are looking at developing hydrogen as a potential export product. And then domestically, we just heard the exciting announcement this morning of the Hydrogen Earthshot, where we're really looking at using hydrogen as an enabler to meet the administration's goals for clean energy production and reducing greenhouse gas emissions. So the hydrogen technology area, there we go. So the hydrogen technology area encompasses everything from production of hydrogen molecules from various feedstocks and clean energy conversion technologies, through getting the hydrogen in the correct form for transport and storage within the infrastructure, to the final delivery and dispensing to various end uses. And then as well as the on-site storage or onboard storage at the end use when necessary. So it's a very comprehensive effort. One of the major organizational changes we've made since the last AMR is that we've now integrated all of these areas onto one program. So we actually have a very comprehensive program, and we have a very smooth transition from the hydrogen production all the way through the infrastructure to the final dispensing use at the end use. We are an application or target driven office. So we have various targets for the applications. For instance, in hydrogen production, you've heard for years we've had a $2 threshold target for transportation applications. With the announcement of the Hydrogen Earthshot, we've now formalized the $2 a kilogram target for 2025, and we're developing technology-specific goals in order for us to enable reaching that goal. So, for instance, for PEM electrolyzers, we're looking at 70% electrical efficiency, $100 a kilowatt stack cost, 80,000 hour durability, and a total system cost of $250 a kilowatt. To get to the 2030 goal of $1 a kilogram, we're currently analyzing various scenarios to determine what the application-specific goals would have to be to enable us to meet that. As we look at the various applications for hydrogen, we see hydrogen liquefaction as being another key enabling technology, as liquid hydrogen will play a greater and greater role. One of the issues with liquefaction today is that at today's liquefaction plants, roughly 1/3 of the lower heating value of hydrogen is consumed just in the liquefaction process. So we feel that we really need to get the energy requirement for liquefaction down and make it much more efficient. So we have a goal of cutting it in half to roughly 6 kilowatt hours per kilogram of hydrogen, not only at the large scale, but also in the low scale, because we see low volume liquefaction still being applicable. Another area of hydrogen being talked about a lot is for energy storage. For energy storage, what we're really talking about is taking electricity, converting it through a PEM electrolyzer to hydrogen, storing the hydrogen, and then using a fuel cell or turbine to convert it back to electricity, but back on the grid. We have targets of $250 a kilowatt for electrolysis. We have a $1,000 kilowatt target for stationary PEM fuel cells. So the question is, what does the hydrogen storage cost have to be competitive with other energy storage technologies? So earlier, Sunita announced the NREL StoreFast model. So using a version of the StoreFast model, we've been analyzing what does the hydrogen storage cost needs to be competitive with other energy storage technologies. The compressed air is the most aggressive, the lowest cost option today. For us to look at being competitive, we're looking at roughly $5 a kilowatt hour for hydrogen storage to be cost competitive with CAES. If you look at pumped hydro, it looks like we can be roughly twice the cost, so $10 to $12 a kilowatt hour for hydrogen, and be competitive with pumped hydro. So again, these are preliminary analysis, which will be at some point getting information, feedback from stakeholders, and then issuing targets for these other applications. In terms of transportation, we've had these goals for a long time. For light duty vehicles in particular, now we're looking at heavy duty vehicles. We have the threshold target of $2 a kilogram for hydrogen production. If you look at today's technology using electrolysis, we are about $5 to $6 a kilogram, and I'll discuss that more in a little bit. If we were able to scale up the manufacturer and get the manufacturer electrolyzers up into the hundreds of megawatt scales, we project it would be around $350 to $450 a kilogram. For a fueling station, delivery to the fueling station and dispensing of the hydrogen, again, for light duty vehicles, our target is $2. For heavy duty vehicles, looks like we can go to $3, so total dispense cost of $5, and still be competitive. With today's technology and at capacities for today, we're about $9.50 to $11 a kilogram. If we were to scale up the capacity of the stations, we project it would be in the $5 to $8 kilogram range. For onboard storage, again, our target is $8 a kilowatt. At today's volume, our projection is about $21 a kilowatt. And if we get to 100,000 units a year, we're about $16 a kilowatt. So we're still about a 2x higher than what we need to be. So we carried a lot of economic analysis to try to understand what are the drivers and where should we be putting our investments to try to reduce the cost and improve these technologies. For production, a lot of it comes from electric energy. This is looking at a high temperature where we also have a thermal energy input, but the electrical energy is a major driver. While we can't control the cost of electricity, we can control the efficiency of the system and therefore try to reduce the amount of energy needed. The other is the capital cost of the systems. So these are a couple of the key areas we work on: efficiency and the capital cost, but also durability, because we need to increase the lifetime to reduce the total overall maintenance costs. When it comes to the infrastructure, again, looking at an 800 kilogram a day station, the compressor is about half the cost. And then the hydrogen chiller, because we have to pre-cool hydrogen to minus 40 degrees, dispenser and storage, this is the high pressure cascade storage. These each cost, roughly around 13, 14, 15% of the total cost. So we get these four levers which we can work with. You'll see as we go to the high throughput stations, the compressor becomes even more dominant. And then for the onboard storage systems, over half the cost comes from the carbon fiber. And this is looking at the total system from the refueling receptacle all the way to delivery of hydrogen into the fuel cell system, including mounting brackets, pressure regulators, and everything. But still, even looking at the total system, about 50% of the cost, or more than 50% of the cost, is just coming from the carbon fiber that's used in the pressure vessels. So looking at our budget for the last several years, we've had 71 million last year and this year, with about 29 or 30 million going into production and 25 million into the delivering dispense part infrastructure, and about 16 million going into the storage part. This is the team. The team has grown a lot since the last AMR. So looking at the production area, we have technology managers. We have Katie Randolph, Dave Peterson, James Vickers, who joined the team several years ago as a fellow. This last year, we were able to convert him into a federal technology manager. And since last AMR, we've also had Will Gibbons join as a technology manager. The production team is supported by Kim Serpent-Gold, as well as Levi Irvin. Levi actually split between the solo office and our office, so it gives us some coordination with the solo office, and particularly the concentrated solar. And then this fall, we're proud to announce that we have a new fellow starting this fall, Mackenzie Hubert, should be starting with us this fall. On the delivery dispensing side, we have Navastagi, Mark Richards, who again, he's been around the community for many, many years, supporting the office as a fellow the last couple of years. And we just a month ago converted him to a technology manager. And then Brian Hunter. And with the recent movement of Jesse Adams to take over as program manager for technology acceleration, Zarek Colvey is currently the technology manager handling all the storage, but he's being supported by two ORISE fellows, Ashley D. Celestine and Martin Silik, who've been providing a lot of support there. And then Eric Hyber, who's also joined since the last AMR, he provides program support across the infrastructure side. And then Marika Lechko, who started just over a year ago, she provides support across the whole program. So let's talk a little bit about hydrogen production. And when you look at the hydrogen technology track, the orals for hydrogen production will be all day Thursday or Tuesday, and for the first two sessions on Wednesday. So when you look at hydrogen production, we heard this morning from our colleagues at Fossil Energy talking about use of fossil resources to produce hydrogen with carbon capture, utilization, sequestration to make it clean. But our office is really focused on these clean energy pathways. So we look at biomass, including waste for conversion to hydrogen, and then we look at water splitting. So low and high temperature electrolysis and direct solar water splitting, which includes solar thermochemical and photoelectrochemical. So I mentioned that our current cost is $5 to $6 a kilogram. If you take grid electricity at 5 to 7 cents a kilowatt hour with a high capacity factor, and you take a conservative capital expense of about $1,500 a kilowatt, that's where the $5 to $6 come from. There's been a number of reports in the last year or so looking at hydrogen production through electrolysis. And if you look at the capital expense that they've come up with, it ranges from about $750 to $1,400. So if we took the more intermediate cost of $1,000 for the CapEx, we're still at the roughly $450 to $550. If we actually looked at real renewable energy cases, so this is from the annual technology baseline report for 2020, and look at renewable energy and the 3 to 4 cents actual cost for renewable energy being generated from at these sites with the lower capacity factors and using that middle of the road cost, we're still coming up in the $4 to $6 range. So that's why we're very comfortable saying that the current cost of renewable hydrogen generation through electrolysis is $5 to $6 a kilogram. But now with the announcements of the hydrogen energy Earthshot or the hydrogen Earthshot, the question is, how do we get from the $5 down to $2 by 2025 and then eventually to $1 by 2030? So the levels if I can go back. The levers we have, first, we don't control the cost of electricity. However, we can control the electrical efficiency. So we're really targeting improved efficiency for electrolyzers. We're also looking at low capital costs for the systems, improving the durability, which will help lower the operation and maintenance costs. But we also need to get low cost manufacturing. And then we also need large scale manufacturing. So we need to get the deployment of electrolyzers up so we can actually increase the manufacturing capacity across the country. So for PEM, this results to get to the 2025 target of 70% electrical efficiency, $100 stack cost, 80,000 hours of durability with an overall cost of $250. And with a reasonable electricity cost, we project that we'll be at the $2 a kilogram at that point. And for solid oxide, where now we have a thermal energy input, we get really high electrical energy efficiency, which is one of the advantages of solid oxide electrolysis. Again, with $100 stack cost, a 60,000 hour durability. So for a total system cost about $300, again, we project would be at the $2 a kilogram. And as mentioned, we're looking at various pathways to get us from the $2 to $1 a kilogram. So what's the approach? I like to describe our approach as a layered approach. We start off with a foundational layer, which is looking at advanced materials. So this is looking at improved membranes, catalysts, ionomers for electrical and ionic conduction. So all the materials to go in. And this work has been carried out the last several years through the Hydrogen National Lab Research Consortium. And then the next layers up is the advanced components. This is where you take these materials, you integrate them into membrane electrode assemblies. So now you're taking the catalysts and the ionomers and the membranes and integrate them together where we need to get to realize the performance of these materials as a complete system. and make sure that the system's going to function properly and have the durability needed under real world conditions. So that work is being led by our new effort, which is H2New, which we'll be describing in a minute. And then the top layer is really getting to advanced manufacturing. This is where we develop low-cost manufacturing processes to be able to manufacture megawatt-scale electrolyzers at low cost and meet the durability and performance that's been developed through the hydrogen, H2New, and the lower level research efforts. And this we envision as all being industry-led activities. So talking about hydrogen, this has been going on for several years. This past year, we actually basically rescoped it, and we've now dubbed it Hydrogen 2.0. Part of the rescoping is reduce the efforts on PEM low temperature electrolysis, as well as oxide conducting high temperature electrolysis, and move those efforts primarily into H2New. However, hydrogen will still focus on the alkaline exchange membrane, low temperature electrolyzers, as well as the proton conducting solid oxide. These technologies are much lower level, and of course, continue working in the direct water splitting technologies such as soil thermal and photoelectrochemical. Over the time frame of hydrogen so far, we've had 11 national laboratories, 10 different companies, and 39 different universities participating in over 30 projects. So it's been a very large collaborative effort over the last 5 years or so. Some of the key accomplishments, recent accomplishments from it, in area of alkaline exchange membrane electrolysis, one of the issues there has been the durability of the membranes, and work at Georgia Tech, one of the Sealing projects, has been able to demonstrate very stable performance for over 750 hours under relevant operating conditions. So this is an exciting new development where we're getting good stable performance over a long period of time. In the case of high temperature, one of the problems with high temperature electrolyzers is chromium poisoning, where chromium migrates from some of the stainless steel interconnects that's used and causes poison of the cell. Work at Nexceris, another Sealing, has shown a productive coating, which is able to give us very stable performance. We don't have the loss in performance you have with no coating. In the area of solar thermochemical, Arizona State University, they've used computer-aided material discovery to identify a new class of materials, which has a second redox site. And this new class of materials, they've actually been able to synthesize the materials and actually evaluate them and shown stable performance, and actually getting higher hydrogen production capacity than the other state-of-the-art materials. And then photoelectrochemical, again, trying to get the cost down with a stable material. People have been looking at perovskites, and work at Rice University has just recently demonstrated a 2.5 increase over in the sun to hydrogen efficiency over the best state-of-the-art perovskite material. And this is integrated in a low-cost 3D printed photoelectrochemical reactor cell. So a big improvement in the efficiency for this perovskite material. The new effort we just launched, which is launching this year, is called H2New. It stands for Hydrogen from the Next Generation of Electrolyzers of Water. It's led by NREL and Idaho National Laboratories, with NREL leading the low temperature PEM activities and NREL leading the high temperature oxide conducting solid oxide activities, being supported by work at Argonne, Lawrence Berkeley, Pacific Northwest, Los Alamos, Lawrence Livermore, Oak Ridge, and the National Energy Technology Laboratory. So this is the group that's really charged with enabling us to meet our overall efficiency goals of getting the cost down to $1 a kilowatt for the stack, improving the electrical efficiencies for the low and high temperature electrolysis, as well as getting the durability up. And in fact, durability is the first major focus. And there'll be initially looking at understanding degradation mechanisms when you integrate the electric catalyst and the membrane ionomers and all the other components into a membrane electrode assembly. And then when you start incorporating that into with other corporates to make up a stack, and developing accelerated stress tests so we can understand the durability in a matter of weeks or months and not having to wait years. How it functions, as we mentioned before, the lower level or layer is the hydrogen, the advanced materials. This group worked with sealing projects where they provided support to sealings using the capabilities at the National Lab. The PEM and the oxide conducting materials were migrating to H2New. H2New is really going to be focusing on the integration into components, and we will be running FOAs and creator calls for groups to join H2New. In this case, we'll be looking for activities that can actually support and fill in gaps within the National Lab expertise. So these will be real partners and not just receive support from National Labs. And then this will all be carried out in close coordination with the manufacturing efforts so that what they're looking at is reflective of what we're coming out of a manufacturing line. And they'll be using an iterative approach doing both in situ and ex situ testing and really and feeding knowledge back into the manufacturing processes. In addition to that, we're looking at the manufacturing. So last year we ran a FOA topic on low temperature electrolysis manufacturing. So this is looking at PEM specifically. We committed $14 million of DOE funds. 3 projects were selected at Plug Power, 3M, and Proton Energy, looking at single piece multifunctional integrated membrane anode assemblies, looking at how to basically incorporate the catalysts and electrodes to fabricate them so we get very efficient use of catalysts and reduce any precious metals required. And then Proton is looking at the porous transport layers and how you can actually optimize the manufacture of the porous transport layers in large area cells. This year, we have another FOA topic on manufacturing, this time focused on the high temperature. We've committed 10 million of DOE funds in this year's topic, and it's really looking at how do we reduce the power count and processing step to manufacture the oxide conducting cells, and how do we can we incorporate real-time quality control metrology in so we can actually improve the quality control and reduce reworks, and with a targeting of getting the manufacturing cost down at $300 a kilowatt. Both of these activities are co-funded between our office and the Advanced Manufacturing Office. And in parallel to all that, we've also been carrying out a separate effort looking at benchmarking and protocol development for all the advanced water splitting technologies. This effort's led by Nel, also Proton Energy. Nel's a parent company, Proton Energy. It was in the State University, Caltech, and Pacific Northwest National Lab. And they were really charged with developing best practices and characterization methods so that we can try to get uniformity on how these technologies are both characterized and reported so that we can get better reproducibility across labs. Part of this effort was to hold annual workshops. Recently, this past year, they held the 3rd annual AWS workshop. This was a virtual workshop because of the pandemic, but actually the advantage of that is we had over 200 participants representing over 15 countries participate. In the prior ones, we were down close to 100 attendees, but being virtual, we're able to get better participation from the international community as well. In the final effort of this current phase of the work, they're finalizing the protocols that have been developed so far. So over the 3 years to date, they've developed the roadmaps for the 4 different water splitting pathways. They've actually drafted and reviewed 45 test protocols, and there's another 25 that are currently under review. And the goal is to get all these published before the end of this calendar year in the Frontiers in Energy. So that should be a big benefit for the research community in these technology areas. And then finally, for production, we're also looking at production using biomass and waste streams. So one of the efforts we've been carrying on for a while is you take a lignosic cellulosic materials. So this could be, corn stalks and cobs, et cetera. And you can use fermentation. And when you run it through fermentation, you get about 4 equivalents of hydrogen per equivalent of sugar. However, you take the effluent because in that process, you also create a lot of other organic byproducts, including volatile fatty acids. If you take the effluent from that and you run it through a microbial electrochemical cell, you can get up to another 8 equivalents of hydrogen per sugar molecule. So you can basically triple the amount of hydrogen produced when you couple fermentation process with the MEC. So through a lab effort with NREL, Pacific Northwest, Lawrence Berkeley, and Argonne, they've been working this technology. Back in 2019, we ran a phototopic, and we selected a project led by Oregon State University, which is looking at improvements to the microbial electrochemical cells. So again, get better improvement in the operation of this system. And in the current phototopic, we had another topic, which is looking specifically at looking at waste streams. So this could include things as wastewater, food waste, brewery waste, et cetera. And so again, we're looking at getting improving the efficiency of the production, getting the cost of the production down, and we expect to be able to make announcements soon. There's a total of about $2 million in federal fund committed to this effort. So moving on to hydrogen infrastructure. With H2 scale, we're now looking at a very diverse set of end uses. It's no longer just looking at transportation. So the transportation, for years we're focused on light duty. Recently, we expanded it to look at heavy duty, so medium heavy duty trucks, but not only on road, but also looking at marine vessels, rail, et cetera. So, these are large contributors in both fuel consumption as well as greenhouse gas emissions. Also looking at synthetic fuels, which could be used for aviation as well as for the heavy duty transportation applications. We also looking at industrial processes. So ammonia, second most widely produced chemical worldwide. When you start looking at metal production, so iron reduction, steel production, cement production, et cetera. These, again, very energy intensive processes and with a large greenhouse footprint. And then also just for power production and providing heat and power to buildings and other operations. Hydrogen can be used in all of these. However, the quality, the pressure, the quantity of hydrogen for these can be very different than for transportation. So this means that we have to be very flexible in the infrastructure and looking at especially the dispensing part. So when we talk about the infrastructure part, we're really looking at once we produce the hydrogen molecule, we have to convert it into the appropriate form for transport and storage within the infrastructure. So predominantly today it's gaseous hydrogen, which is often shipped by trucks, could also be put in pipelines. We also have liquid hydrogen. You have to liquefy the hydrogen, and today it's primarily shipped by truck. There's a lot of activity now, especially for potential for export markets, looking at marine transport of liquid hydrogen, but also you can look at rail. And then there's carriers. This is where the hydrogen is bonded within another material, and depending on the form of the material, be a liquid organic, or maybe something like ammonia, which is a liquefied gas. You can use trucks, you can use ship, you can use rail, you can use pipelines. But then once you get it to the end use, you need to be able to dispense it to the final end use application. So the hydrogen infrastructure technology area, it looks at this entire gamut from converting the molecule to the right form for transport and storage to final dispensing, and especially in the case of transportation, even the onboard storage technologies. So looking at the delivery and dispensing aspects, these oil projects will start in the third session on Wednesday and go through all day Thursday. One of the major efforts we've had in this area for the last several years is the Hydrogen Material Compatibility Consortium, or HMAT. This is really looking at how do we improve the materials and identify what materials are compatible for hydrogen service, and metallic as well as polymeric materials. So again, it's a national lab institute with Sandia National Lab leading the areas of metals and Pacific Northwest leading areas in polymers. So the issue is, how do we improve materials to avoid things such as blistering of polymers used in seals, as well as cracking and other failure modes, and also looking at metals and looking at how do we improve the metals so that we can actually get the cost down and improve the performance of metals. So ideally, they work with the actual producers and actually can work with the actual materials and hopefully the actual products that's used in the infrastructure. So for instance, in the polymer side, they look at various materials that usually include plasticizers or fillers, and then they look at what happens when you start cycling it in service and hydrogen. And in this case is looking at these filler particles, where when you start cycling and you start putting in the hydrogen, you start seeing the formation of voids. So ideally what they do is working with real products from vendors, they're able to identify what are the failure mechanisms or what are the mechanism that leads to the failures. And then by computationally modeling it, they can then look at strategies to help mitigate those failure modes. And so they've actually been able to iterate in this process with actual producers of elastomer seal materials, for instance, and actually been able to improve the materials so we get better service. Similarly with metals, and this is an example where they took 9 different microstructural variants of a single pressure vessel steel, and they're able to actually do a correlation and understand the relationship of the microstructure and the strength and the other properties of the material with its fracture resistance. So again, using this, they're able to identify ways to improve the production of the materials. So for instance, the heat treatment and the annealing temperatures to actually better performance. And so we can actually get longer life and hopefully lower cost from these materials used in service. So related to that is a newer effort. Sunita mentioned this a little bit earlier. We're looking at the blends of hydrogen and natural gas. So, a lot of people wonder, why would you blend hydrogen into natural gas? Well, for utility companies, this is envisioned as a fairly low cost, easy way to start reducing carbon dioxide emissions from their applications or from their uses. A 30% by volume blend of hydrogen and natural gas would reduce CO2 emissions by 10%. So one of the questions we're constantly asked is, well, what level of natural gas or hydrogen can I blend in natural gas? And technically you can go from 0 to 100% blend. The question is, what would be safe and practical? Because when you start blending hydrogen into natural gas, we have A, material compatibility issues. B, we have issues with, for instance, combustion characteristics, because the combustion of hydrogen is different than natural gas. The energy content is different. But another advantage is the fact that if you look at US, when you look at the transmission network as well as the distribution network for natural gas, we have over 3 million miles of pipeline. So this is a way to actually produce a very large amount of hydrogen and put it into the natural gas pipeline. So this is one way to get rapid scale up of hydrogen production. So if we just blended 20% of hydrogen in natural gas, we could essentially double the renewable generation. So we have the HMAT consortium working, understanding the compatibility of materials in a blended situation. In the CRADA call we ran this past year on this, we had a very large response. Currently, we have over 20 stakeholders that are involved in this effort, and we have a lot of other companies which are asking to join. So there's a lot of interest in this high blend effort. The other area we're looking at is the heavy duty refueling station components. So as I mentioned earlier, when you look at heavy duty stations, so this is looking at being able to refuel 50 heavy duty trucks at Summer Bar in 6 hours. The cost is dominated by the compressor. And then the high pressure cascade storage is the second most costly element. So, we are understanding this. We are looking at other station designs, looking to see how we can we mitigate the effect of the compressor. And in response to trying to develop both the station designs and components for heavy duty refueling, we ran a CRADA call in FY20, from which we selected 5 projects at roughly $10 million DOE funding, looking at station designs, as well as doing some R&D and cost analysis on the refueling methods and especially chiller designs. This year in the FY21 FOA, we had a topic looking at the domestic supply chain for high flow hydrogen stations. These are going to be 3-year projects with about $8 million or up to $8 million of DOE funds being committed, and looking at all the various components. So compressors, chillers, nozzles, hoses, meters, etc. And again, we expect selections of these projects to be known soon. So moving on to the hydrogen storage aspect. In 2019, we updated our baseline cost projections. So 2013, we were projecting about $22 a kilowatt hour at 100,000 units a year. Today, we're about $16 a kilowatt hour for 100,000 units. So that's about a 30% reduction we're seeing between 2019 or 2013 and 2019. And this is for the whole system. So this includes the fueling receptacle, all the way, the gas manifolds, all the way to the pressure vessel, including inline tank valve, the pressure regulator, and everything required to mount the system and deliver the hydrogen to the fuel cell. This is for a single tank design. However, all the cars up to today actually have multi-tanks. So the pressure vessel with the in-tank valve is what we call the repeat unit, because that's the part that has to be replicated every time you put another tank in. So we just took that repeat unit, which is the pressure vessel and the tank valve. This is the cost breakdown. So we go from about $16 to about just under $12 a kilowatt hour when we do that. However, the carbon fiber has gone from a little over 50% to over 70%. So this kind of gives us an idea of just looking at the pressure vessel itself and the tank valve. When we look at heavy duty trucks, we do not yet have a baseline system defined. People are looking at putting hydrogen behind the cab, on outside the rails, inside the rails. People are looking at anywhere from 60 to 100 kilograms on board storage. So we have not yet defined that total baseline system. However, we can take a repeat unit. So this is looking at a tank that would fit behind the cab with about a 20 kilogram usable capacity. When you do the same breakdown, we see we're a little bit cheaper, about over $1 less per kilowatt hour. Carbon fiber is about 77%. The other tank components, such as the boss and the liner and the dome caps, they essentially go away. But it's really the resin, the lining, and the carbon fiber that dominates. So from this, we project that we're probably going to be a little bit less than this cost for a total system for heavy duty trucks. And the strategic analysis presentation on Friday will show that they're just about $12 kilowatt hour for a 60 kilogram system based on one of the systems they're looking at. But it really emphasizes the impact of carbon fiber. So our major effort around this is how to reduce the cost of carbon fiber. 2017, we ran a photo topic and selected several projects looking at reducing the cost of the precursor, which counts for about 50% of the total carbon fiber cost. These projects are wrapping up now. There has been some delays because of the COVID for the last year, so Oak Ridge will be extended for a while. But the two university projects are essentially wrapping up. They've all made progress. However, we're not quite at where we had hoped to get to. But they've shown potential for at least 18% reduction in the carbon fiber cost. In the 2020 FOA, we ran a new topic looking at going from the precursor all the way through the conversion to carbon fiber and into the tank itself. So these teams require to have a carbon fiber manufacturer as well as a tank manufacturer. We selected 4 projects from this effort. University of Kentucky is continuing with to further improve their hollow carbon fiber efforts. We have University of Virginia, which is looking at a non-polyacrylic nitrile low-cost precursor fiber that's been developed in some other federally funded programs. Hexagon Lincoln, which is a tank manufacturer itself, is looking at an optimized precursor fiber spinning and conversion process, as well as improved utilization of the fiber in the tank itself. And then we have CCSC, which is the nonprofit that runs the Institute for Advanced Composite Manufacturing Innovation. They're leading an effort looking at the melt spinning of precursor fibers, again, to get the dramatically reduced cost. These efforts are being run as a 2-phase effort. The first phase is for 2 years. All 4 projects would participate. At the end of those 2 years, the properties of the carbon fiber produced, as well as projections of a tank the performance of a tank using those carbon fibers will be evaluated against criteria which have been developed, and the project which best comes out against the criteria will be selected to continue to phase 2, which is a 3-year effort, at the end of which they have to be producing tanks and demonstrating performance of the actual tanks. Total commitment for this effort is $15 million and is being jointly funded by our office, the Advanced Manufacturing Office, and the Vehicle Technology Office. Bulk hydrogen, again, we're looking at bulk hydrogen, and for amount of time, I'm not going to go through a lot of effort or a lot of detail here, but strategic analysis, we're presenting on a bottoms-up cost analysis for a liquid hydrogen storage should be usable for stations, so we can actually then start identifying where are the key cost drivers, so we can, where we may want to put effort to reduce the cost of liquid storage. But we also are currently finalizing negotiation of a new project being led by Shell, looking at extremely large volume liquid hydrogen storage systems. These are the type of volumes that people are expecting to be needed for an export market for hydrogen. To put this in context, we're talking 20,000 to 100,000 cubic meters. Currently, the largest liquid hydrogen storage vessel in the world is in final stages of construction at the NASA Kennedy Space Center. That is 1.2 million gallons, which converted is less than 5,000 cubic meters. So we're talking about systems which are 4 to 20 times larger than the current largest existing liquid hydrogen storage system. And we're targeting CapEx, which we benchmarked against liquefied natural gas storage systems. We're also looking at intermetallic hydrides for stationary storage, which offers advantages of lower pressure, lower cost operation. And so these are national laboratory-led efforts. And right now, we're, at least from a model perspective, we're seeing some very good performance here. For carriers, we're looking at hydrogen carriers. Some of the key efforts in carriers include a centralized production of the carrier. So this is where the carrier is produced, taken to the end-use application, the hydrogen is released, and then the spent material is brought back in case of a two-way, or like for one-way such as ammonia, the nitrogen be vented. And we're also looking at carriers where we could actually do the regeneration on site. So this is where, for instance, you use renewable energy, you generate the carrier. When you don't have sufficient renewable energy, you use the carrier to produce hydrogen to supplement the renewable power. And then when you have the excess renewable power, you again regenerate the carrier. And doing some benchmarking against other hydrogen storage technologies. So this is a number of carriers with a coupled to a PEM fuel cell, looking at energy density versus the power density. Here's where redox batteries fall. And then we have 250 bar, which is a common pressure for storage of hydrogen and liquid hydrogen. And you can see we have carriers which are actually outperforming a number of the conventional ways of hydrogen storage right now. And then a couple of the other research efforts we have right now, looking at, for instance, this is an analysis led by Lawrence Berkeley with Argonne and Pacific Northwest, which is looking at the tyrene methyl couple to enable a 24/7 operation of a totally renewable powered steel production, where you take the excess renewable energy to generate the carrier, then we don't have sufficient renewable power, you use the carrier to supplement that. And then we have a second effort, which is same team led by Argonne, looking at dibenzyltyrene, some other carriers in a microgrid application. And then Highmark is the big lab consortium we've been running. It's been going on for several years now. I'm not going to go into details here again for the sake of time. A couple of key accomplishments. This is one new exciting one. For hydrogen adsorbents, one of the issues with hydrogen adsorbents is that the binding energy of hydrogen is too low. So after operating cryogenic temperatures, it's been projected we need a 15 to 25 kilojoules binding energy to be at room temperature. They just reported in the Journal of American Chemical Society, JACS, a new vanadium MOF material, which actually has an isosteric heat of absorption of 21 kilojoules mole, right in that ideal range. The capacity is still low, but it's still 38% better than compressed gas, and it's a 27% improvement over any of the other state-of-the-art adsorbents at room temperature. So that's an exciting new development. And again, just for a matter of time, another exciting development. This is actually one of the ceiling projects, University of Southern California, working with PNL, have shown an iridium catalyst for the decomposition of formic acid, where they can get very high rates, but also directly generate over 170 bar pressure from the decomposition of formic acid. So this could be a big advantage in applications where you need higher pressure, because you could eliminate some of the compression stages to reduce the cost of compression. So as I wrap up here, we are a very collaborative effort. We collaborate across the DOE. We collaborate across the government, as well as internationally. And this is just a number of the milestones over the last several years. And then finally, just like to announce that we are still looking for 2 new fellows. So if there's anybody out there that'd be interested in joining our team, we have openings for 2 new ORISE fellows, specifically helping out with the hydrogen production and the building dispensing infrastructure activities. So if you're interested, please, here's the site. If you Google ORISE Science and Technology Policy Fellows, you could probably find this. So with that, I will end and thank you all.